by apologizing for the confusion, but the talk is coming up. Okay, so yeah, so again, I will like to thank the organizers for organizing this very nice meeting, or continuing to organize this nice meeting. And I would like to talk about networks. Networks of agents with a degree preference. This work has been done with Royce Sia in Virginia Tech and Kevin Butler at University of Texas. Details can be found in this published article, but I'd like to describe to you roughly what we have done. Okay, so the model we discussed is called, we have just called the extreme introvert-extrovert model. So it is a model of social network in which there are two types of agents. One are called introverts, one are called extroverts. And they are extreme introverts or extroverts. The introverts don't want any contacts. Extroverts want as many contacts as possible. And given an opportunity, an agent has a choice of updating his links. So an introvert, if there is a link, he will delete one link out of the ones which are there. An extrovert will add a link to an unconnected agent. So then we studied this. We studied as a simple model of a model with dynamical links, in which the links keep on changing in time, and we are trying to look at the steady state of systems with such dynamical networks. Okay, so we studied three variations. One is called the random this random XIE model. In this model, when you encounter you pick an agent at random and give him a chance to update. Now, suppose he's an introvert, but he has some links because other people connected to him, then he deletes one. So he deletes one of the links at random, one of his links at random. And extrovert will add a link to one of the unconnected agents fully at random. Okay, so that we call the random XIE model. In this case, we have studied the steady state of this network, and there are some interesting results about the large N limit, which I'll tell you about. But then we studied some variations of this model, which we call the Egalitarian XIE and Elitist XIE model, where we change this random rule. So instead of random, suppose you are an introvert and you are trying to delete a link. Which link will you delete? So maybe the introverts have a rule. They say they want to distribute the links as much as possible amongst all the agents. So they will delete the link to the most connected extrovert. Or vice versa, you can have a different rule, which is the opposite of the previous one, which we call the elitist model. It is like this, that I'm an extrovert and I want to connect to a person. So I want to connect to the person who is most connected because he's the star. So everybody wants to connect to the star. Okay. So if you study all these kinds of different rules, one can see different phenomena and see what happens. That is our general. Okay, so first let me tell about this random XIE model. So there are n agents, n introverts and n extroverts. At each time step, we choose either an introvert or an extrovert, and you can choose them with a bias towards one or the other. So Z is a parameter which chooses the bias, whether you choose introvert or extrovert. Introvert will cut links at random, extrovert will add links at random, and you keep on picking people at random and giving them a chance to update. What happens? So we look at the steady state with fluctuations. And in the steady state, there are only links between introverts and extroverts. Because even if you started with a link between two introverts, sometime or the other they will cut it and they will never add. Similarly, between two extroverts, in the steady state, there is always a link present because they will sometimes add and not disconnect. So the only links are between introverts and extroverts. There are n squared such links. Okay, so the model has a symmetry between introvert goes to extrovert, Aij is the adjacency matrix which says 1 if there is a connection from ith introvert to jth extrovert. And so you flip A to 1 minus A and Z to 1 by Z and introvert to extrovert. So it's some kind of Ising symmetry. So you can ask what is the steady state of this model. And it turns out that you can write the probability of a configuration in this model in a very nice, simple and symmetric looking form. So if you look at a configuration in which the ith introvert has degree pi and qth extrovert has degree qj, and you ask what is the probability of this particular configuration, it turns out that the probability is proportional to pi factorial multiplied over all I n minus qj multiplied over all j, and there is a normalization factor. And if you have a bias, it's z to the power pi product. So it looks like a very nice formula multiplying lots of products of factorials, and so it's a nice weight, and can one do some interesting statement with this. The proof of this is fairly straightforward. Just check that if detail balance condition is satisfied with these rules. Okay, so we can look upon this model as n squared matrix with elements 0 and 1 which keep on flipping. So it's a dynamical Ising model. So what is the partition function of this Ising model? Well, we know the probability of a configuration, that is this. And so you can define the Hamiltonian as a log of the probability, and that just becomes this. So it's a Hamiltonian in which the energy depends on the sums over spins of, but the function is only a function pi and qj, which are row sums and column sums of the matrix. Now, if I recall, in the standard mean field theory, if the Hamiltonian depends on the total magnetization, then it's easy to solve. Here, you have a Hamiltonian which depends on row sums and column sums of the square matrix. So it's a little bit more complicated, but can one solve this using mean field techniques? Because the number of variables is n to n, it's much less than n squared. And so this is all it says. It's the adjacency matrix and can be thought of as Ising spins. It has row and column sums. And this condition allows us to determine log omega exactly in the large n limit. So in the large n limit, the fraction of occupied links jumps from 0 to 1 as z crosses 1. So z was the bias parameter. If you bias towards the introverts, then you have no links in the steady state, more or less. And if you have z is above, then you have many links. Basically, it's a fairly straightforward thing. People keep on adding links, and introverts don't get time to delete them. So, you know, everything gets clogged. So this phase transition is quite sharp in practice. If you have z equal to 100, and the bias is 0.975, then already the number of connected links is only 1 upon 25. You know, so by adding 1% of change, you are getting such a large change. So that's also something one can try to understand. Okay, so exact results for the XIE model. The n minus qj factorial can be approximated as n factorial divided by n to the power qj times a slowly varying function of q. So then you can write the h effective as h0 plus h int. H0 is log pi plus pi as this kind of stuff. H int is a weakly changing function of q. Under this h naught is sum over I, but there is no sum over, there is no dependence on j. So different rows become independent. And so you can solve it exactly. And when you do that and do all the calculation, this log omega, which was the partition function, becomes n log n factorial plus n. So this is the series expansion in powers of h int. The first term is of order n squared log n. That is because the Hamiltonian is non-extensive. The next term is of order n. Next term is of order 1. Next term is of order n to the power minus half, and we didn't go further. But you know, in the large n limit, this perturbation expansion is very well behaved, and we don't need to go further. Okay, so this is about the elitist. Elitist agents, and so I already told you what are the elitist and egalitarian. So for the egalitarian agents in the steady state, we can work out. It turns out that if Z is less than 1, an introvert will have either 0 or 1 contact, and the fractional number of introverts is 1 minus Z. You can tell what are the distributions. The most interesting case is at the point of phase transition, which is Z equal to 1. The total number of links in the network, there's a random walk with reflecting boundaries from 0 to n squared. But any time the degree of a link has a small spread, either the degree is k or k plus 1, but k is a changing in time. So by their cooperative action, the agents are able to keep the degree of inequality between different agents small, even when the overall conditions in the system are undergoing very big changes. Okay, and this is a picture of the square matrix. 0 and black are the different entries, and you can see it goes from all white to all black as time varies. You don't see too much structure in here. This is a more sort of explanatory picture. Here there are actually 4 graphs of the time history of connections of 4 different agents. 2 of them are introverts, 2 of them are extroverts. But they are all the same. You cannot distinguish. You only see one color because the lines are falling on top of each other. And yeah, so now, so that just shows that the degree at any given time is the same for introverts and extroverts, and different agents have the same degree. So for the elitist model, there is a very interesting instability. Start with all links absent, then an extrovert will add a link to some randomly chosen agent, then all later extroverts will add to the same agent. Because they add to the one who is most connected. Right now that one is the most connected. So once this person's degree becomes n, then the crowd chooses the next superstar, and then everybody connects to that, and so on and so forth. And then what happens in the steady state? This we will skip just now. So you have an incidence matrix. In this case, I put ni, ne not equal. And you don't see too much structure. Now it looks complicated. But if you reorder this matrix by putting the agents in the ascending order degree, then you get a very nice picture in which all the ones are here and all the zeros are here. Okay. And so the sorted matrix has a single block with no holes, all ones on one side, all zeros on the other side. And this boundary fluctuates with time. It can be written as an interface model, but the rules of the evolution model are slightly complicated, and this model is not exactly soluble. And this is the time trace of the similar type, but now you can see different colors. So individual agents' degrees undergo very large changes here. But the full structure, and this is a zoom up of the same, shows interesting behavior. This is the summary. So we studied a model of dynamically evolving links. In the random case, the partition function has interesting structure. For elitist model is equivalent to a surface growth model, and we hope that these kind of models can be used in some kinds of problems in economics, social sciences, biophysics. And I can explain the biophysics one because that is a skipped slide, but there is no time. So we think that it is in the Edwards Hemsley-Wilkinson universality class, but we have no proof. That is because it is unbiased, it's not a preferred direction of growth. Our results are consistent with that hypothesis, but we cannot. Yes, it's a first order transition. Yes. No, because the behavior is very different. Here there is actually a discontinuous jump from almost no activity to everything full. Voter model has much more structure, and most of the time half the agents are one type, half the agents are other type. That's a, that's like an Ising model. This one is like a first order transition. Yes, it is a bipartite graph. It is a random bipartite graph, but with a particular set of correlations. Yeah, you can compute several more, but we stopped at some stage.